This is problem 20 from chapter 18. If P is equal to 200 newtons and the 15 kilogram uniform slender rod starts from rest at an angle of 0 degrees, determine the rod's angular velocity at the instant just before theta is equal to 45 degrees. So theta is this angle here. We're starting with the rod at rest, and we want to find the angular velocity just before theta is equal to 45 degrees. So let's say final kinetic energy is when theta is equal to 45 degrees. And for final kinetic energy, I'm going to use equation 18.7, where I have the moment of inertia about the instantaneous center of zero velocity. In order to do that, I have to find where the instantaneous center of zero velocity is. So this is for our final kinetic energy at an angle of 45 degrees. So if we call this roller A and this roller B has a velocity which is at an angle of 45 degrees, and roller A, right before it gets to this point, the velocity was in the horizontal direction. So right before it gets to 45 degrees, the velocity is like this. And so remember, to find the instantaneous center of zero velocity, we can draw a line which is perpendicular to the velocity at roller B, and now the velocity at roller A, and where they intersect is the location of the instantaneous center of zero velocity. I didn't do a terribly good job of drawing this picture. If this angle is 45 degrees, this angle is also 45 degrees, and this angle is 45 degrees. Which means this must be a right angle, and also this distance from roller B to the instantaneous center must be the same as the distance from roller B to roller A, which is 600 millimeters. So this distance is supposed to be 0.6 meters because it's the same as the distance that I have here. Now remember, from the parallel axis theorem, I can say the moment of inertia about the instantaneous center of zero velocity is equal to, now in the parallel axis theorem, this is the moment of inertia about point G, but it doesn't have to be the moment of inertia about point G as long as the old axis and the new axis are parallel to each other. So I know the moment of inertia about one end of the slender rod, or I can look it up in the back of the book. And about one end of the rod, that's 1/3 ml squared. So this is equal to 1/3 m. The length of the rod is 0.6, so that's 0.6 squared. And then from the parallel axis theorem, plus m times the distance between the old and the new axis squared. So that's another 0.6 squared. So that is 4/3 m times 0.6 squared. Okay. And if you want to put the mass in, the mass is 15 kilograms. So this is 7.2. And what am I looking for here? I'm looking for the angular velocity. So I could put the 7.2 in here. Then I have to find the change in gravitational potential energy. Well, for the change in gravitational potential energy, I'm looking at how the height of the mass center changes. So the mass center was here. Initially, the angle was 0 degrees, so the change in height would be the distance from here to here. This is the length of the rod, that's 0.6. So for this triangle here, from roller A to the mass center, that would be half of 0.6, that's 0.3. And we want the vertical component, and this is a 45-degree angle. So for the change in gravitational potential energy, we have m times g times 0.3 times sine of 45 degrees, which is 0.7071. And the mass is 15, g is 9.81, so this is 31.215. Then I have to find the work done by non-conservative forces. So I have a force P here. It's a 200 Newton force, and if the rod starts off horizontal, then roller A is going to be a distance of 600 millimeters away from its final position. So roller A moves through a distance of 600 millimeters, which is 0.6 meters, with a 200 Newton force acting on it. So from equation 18a, if your force is constant, you can pull that outside, so it's just force times the distance. So that would be the 200 Newton force times the 0.6 meter distance. And that is 120. So now we can just take everything and put it in our work energy relationship. So T1 is 0. The work done is 120. T2 is equal to 1/2 of 7.2 times omega squared. And the change in gravitational potential energy is 31.215, and we are ending at a higher height than we started from, so the change should be positive. So you can take this and solve for omega, and you should get 4.966 radians per second for omega.